All right, welcome to another Friday. We have again Kevin join us. He just got back from a trip, which hopefully was good. So we'll get back to the normal schedule and talk about Bitcoin and specifically everything sCrypt related. So in this week, I think probably going to do the same agenda we did before. So we released some good technique. I will just go over it, and if you have questions, you can ask me about it. And then afterwards, if you have any other comments, anything, we can talk about it. Okay, so let me share.
Sounds good.
So I think earlier this week, we published this technique. Basically, if you've been to our blog in the last two episodes, we talk about this concept. You probably heard about it, right? I call it pay to contract hash. Basically, it's a little bit similar to pay to script hash for people who have heard about it, pay to SH, but it's more general and it does not require any consensus change. So it can just run on top of the original Bitcoin, which is Bitcoin SV today. So we are here, we use this technique, pay to contract hash, to break apart big contracts for many cases. So one of the, I wouldn't say feature, a bug, is one caveat of using sCrypt, essentially is script. You have to, if you want to do any kind of loops, you have to unroll it before you send it to the blockchain, because in script, to prevent DDoS, right? There's no jumping instruction. There's no opcode that lets you jump backward, because otherwise, attacker can create something very small program, and then you go to an infinite loop. That's not good, right? The whole network can grind to a halt. You don't want that to happen. So the caveat for that is everything, if you want to do it multiple times, you have to just repeat it in the code as it is that many times. So a lot of times, for example, if you want to do some big loops, you don't know how many loops you're going to have, right, in advance, because they may depend on runtime parameters. For example, whatever in the unlocking script, right? You don't know what the spender is going to provide in unlocking script. So that means when you're doing loops, first of all, you have to know how many times you're going to loop. There's going to be upper bound. And second, this upper bound, you cannot set it too low, because otherwise, for example, if you want to compute some, let's say Merkle tree root, right? Because Merkle tree, you have to loop the number of times equal to the height of the tree, right? You see what I mean, right? If it's like,
yep.
Let's say you are proving some, SPV in script, right? So if you want to do 10 loops, that's only give you like, at most, one block contains only 2 to the power of 10, which is about 1,000 transactions, right? So if you hardcode 10, what if there's a bigger block found? You have, let's say 1 million transactions, then this one can fail, right? I think in general, if in a traditional programming environment, that's probably okay. You can then update it, but here you cannot update it afterwards, right? And because you deal with money, that means the money is locked forever. You cannot retrieve it, even the good parameter, the solution to it. Now the money gets stuck and it essentially is burned. So for these two reasons, the loop has to first set it to be known in advance, and also it has to be very conservative. You want to cover the worst case scenario. You want to, for example, if you're computing some kind of like a Merkle tree, you may want to put it to 30 loops. That covers you 1 terabyte blocks, right? Which is a lot. I think at least in the near future, it's probably be okay, right? So which brings you the downside, because most of the time, in the short term at least, your block is not going to be 1 terabyte, right? But to cover the 1 terabyte block, you have to loop 30 times, which means your script is going to be, unnecessarily big. So you have a dilemma here. If you set too small, you may fail and your money may get burned, right? If you set too big, the transaction size may become unnecessarily big, and then you have to pay more fees. So basically using this technique, you can have the benefit of both. First, you can have a kind of like a dynamic loop count, but also you'll be sure, even if the worst case coming, you can still unlock. Is this problem at the high level clear to you?
Yeah, it is. It's no, but now I'm curious how this works. Are you able to? I'm reading the blog right here. How does it work? Are you able to? Is it like, emergency situation? You could plug something in, but otherwise, like I don't.
Kind of like it's almost like you are loading a library, because if you remember our pay to contract hash concept, so basically, you have a. We can go to another article. I think the Winter call. So basically, if you remember the Bitcoin contracts, each input.
Oh yeah.
Yeah, you remember this article? Have you seen this?
I remember it. I mean, I never totally understood it, but I remember kind of how we were able to. How do I explain this? It was like I should really stop referencing the old Ethereum stuff, but I made the analogy where you could. Like in the past, people wanted to upgrade their contracts, and so they'd have some sort of it's like a pointer basically to a different contract, but then they could update it and stuff. That's what I remember this being like a little bit. And so, yeah, that makes sense. Is that if it's referencing something else and you could update the thing that it's referencing,
yes,
you could plug in maybe a different,
yeah, that's exactly
different variable for the loop.
Yes.
Cool.
So basically, we have called it because each input is unlocking a separate contract, right? Because that's how it works, right? The contract, each input is unlocking the locking script here, which is the contract here, right? So when you I think you can think about almost like a library call. If I'm this, I have an input, this unlocking the caller contract. In this caller contract, in a way, I can reference whatever in my neighbor's input. And then here, I can use the hash of this contract to reference it. It's almost like you are calling a library, but instead of using the name, right? Because we don't have a name in script, native script. But we do have the raw script. We can hash it. We can use that as a almost like a unique ID, right? Reference to call a certain library or function.
Cool.
So in this way, we reuse the same technique. Come here. I just gave another example. I think to give the example here is if we have a last article, we talk about you implement SHA-256 hash in sCrypt directly in sCrypt. So in that case, I mean, because you're hashing and you have to divide the original data into multiple chunks, right? Each chunk, you run the kind of loop body, right? So if you want to hash the whole thing, you have to loop the number of chunks, but you don't know that how many chunks you're going to have in advance, right? So that's why you have to set the chunks to be very big, because otherwise you cannot.
And just for people watching, this is in calculating. It's like kind of a, nerdy thing, but if you understand how a hash function is calculated, it could be on like any size file. So you could hash just a small image, a small piece of text, or a huge movie. And obviously there's going to, and the way it works is by breaking that into chunks. And so if you're doing a huge movie, you're gonna have to loop like, however many thousands of times probably, But if you're just doing a small piece of text, you're only going to have to loop maybe once or twice. And so there's a variable thing here, which is what you're trying to solve.
Yes. And each chunk actually adds about 60 kilobytes. So that's big. You don't want to, for example, if you want to only iterate one chunk, but sometimes the chunk may be huge, right? Maybe you have 10 chunks, but then you have to hard code the loop count to be 10, right? Which adds you 600 kilobytes, which is not ideal at all, right? But using this technique, you can break apart the whatever contract you are using. For example, at the last article, we use increment log time split. Log time. We just split this contract into two parts. One is the original with the call logic, and everything there you're going to check the log time. And we take the part which has a lot of loops. We put it into another contract. It only does the loop. We put it over there. So we can use the contract call, basically P2CH hash technique to call this loop. So basically, the whatever original contract you're going to have, you just cut the part where it does a lot of loops, you put it into another contract. So it's almost like you are taking apart the original one and break it into multiple parts. Once you can do this, because here this is where the loop is, right? This is your main contract. And then you can dynamically change how many loops you are going to use here, right? Because this is a separate contract by using different hashes. For example, here, right? I call the callee contract hashes. Basically, in this case, in this example, let me show you first the main contract, right? It's the same with the last one. Everything is the same, except now I put this part. I use the pager contract hash technique to call another contract called partial SHA-256. So in here, you can see this contract, the new contract, is pretty much, this code is actually taken from here. You can just copy and paste it here. That does all the loops, right? This gives you how many chunks you're going to hash. And then this is the constant number. So what you can do off chain, you can compute you can compile this thing when it's 2 and then hash it, right? And then you can compute it, change it to 3, you hash it again, you change it to, I don't know, 20. Then you can hash, you can get different hash. For each hash corresponds to one specific number of chunks. Make sense?
Yep.
Okay, so after you have all this hard-coded, almost like hard-coded number of chunks you can support, you can just put it in here. This basically means what are the number of chunks you can support. So you can support up to 3 or 10, because there's no, if you notice, there's no loop in this main contract anymore. So you can set it to be, you can set here, oh, I support 3, let's say I support 1 chunk, 2 chunk, and then 20 chunks, right? This code will not bloat. And if you only need 1 chunk, you use you code hash for the first one, and then if you if sometimes the per image is very big, you have 10 chunks, then you can call the one with 10 chunks. But here's the idea: for the biggest one, you still use big locking script because that's unavoidable, right? But most of the time, you are not using the big. You don't have to use a big chunk number. And then they'll save you, right? It's like before 100% of the time, you have to use, let's say 10 chunks, right? Because otherwise you may fail. But now, since most of the time, maybe 10% of the time you have, or maybe even 1% of the time you have to use 10, but most of the time, 99% rest of the time, you only have to use one chunk, right? That's give you almost like a 10 times saving, almost, right? I mean, they have a, when you use a pay to contract hash, you have some overhead, but that's compared to the, what's the loop body is almost negligible. Does this make sense?
So when do you,
approach?
yeah, so you're still having to set the upper bound, but now with this new technique, instead of putting it directly into an unchangeable script, you could kind of, I'm trying to understand when do you set this, when do you set this upper bound?
So here,
Like it's not going to be in the main script, but it's going to be in another script that you still have to set, right?
Yeah, the library. In this case, I can
Okay, the library.
Yeah. So this I can set it to be 2, 3, 4. Every time I set it to a specific number, I can compile it, right? It's going to give me a unique script, which I can then hash. And then using the pay to contract hash technique, I can use this hash to refer to it, to reference it.
And so you get to put that in a parameter, like
Yeah,
as a call. Oh, okay, cool.
So this is all hard coded.
So when you're actually calling the contract is when you could actually input this variable.
Yes, like basically this one.
Okay, cool.
How many chunks is going to be in the callee, the library contract?
Got it.
It's almost dynamic.
Cool, yeah.
You are dynamically loading, right? If you have only need one chunk, you use the hash for the first one. If you use 2, you use second. If you use 10, you need 10 chunks, you use the last one. In this case, I'm only using 3 hashes. Clear?
Yep.
Yeah, so that's like a generic technique. You don't have to confine it to the scatter physics. It's any big loops, right? If you have a big loops in some contract, and then you can take out this. And if it's the loop count is not fixed, and you can vary a lot, right? Maybe most of the time it's very small. It's like kind of like a, I don't know if you remember this, how do we encode numbers in script, right? We have this push data opcode. Do you remember?
No, I don't remember that one, but
Yeah,
I do remember push data.
Yeah, it's a variable encoding, right? It's very similar there. Why don't you always use push data 4? Because you can push up to, the length can be up to 4 bytes, which is almost like a 4 gigabytes, right? But most time you don't need that big number, right? So that's why you can, for smaller number, you don't need 4 bytes to encode the length. It's the same idea here. Because most of the time you are not going to reach the worst case scenario. So if this is the case, you can break apart your contract. You can separate the looping part into a separate contract and then compile it with different loop count and then hard code this loop counts, the hash into the main contract. And then you can use pay to script contract hash to reference it, almost like a dynamically. Because when you unlock this one can be changed, right? You can choose, chunk of 1, chunk of 2, chunk of 10. It's fine.
Got it. And then the primary thing is just to save costs, perhaps.
Yes.
Yeah.
In this specific example, actually this saving is big because if you use every chunk you hash, it takes about 6 kilobytes. So you are saving a lot of fees actually. It's about 6 kilobytes. Yes. I think, yeah, wow. That's also the scenario here. If every loop only take you 6 bytes, you probably won't bother with this technique, right? Because anyway, it's small. It probably only makes sense when each loop takes you a lot of space. And the worst case is like many times bigger than the average case. So only under these scenarios, I could imagine it makes sense. You can save by using this technique. Don't use it everywhere. You should have a loop, only two 2 loops, and each loop is like 10 bytes. You probably will not save much because anyway, it's not big. So, and I just talk about the loops, right? That's one typical scenario why the contract is big. Another one is also very typical. It's very could be, you can see it a lot of times in production. Basically, when you have a huge contract, why it's big? It's not only because of the loops, also because you have many ways to unlock it. Right? For example, you can, if Alice and Bob both sign, you can unlock it. If Alice and signs and he knows some hash, or if some timeout, right, some lock time has been reached, you have many ways to unlock, right? In this case, this also can grow big because each branch is a unique way to unlock. And when you have many branches, this contract also can become big. But here's the thing, right? Eventually, you're only going to unlock with only one of these ways, right? Because your UTXO, you cannot unlock it in twice. Otherwise, it's a double spend, right? So each public function here means a unique way to unlock it. And eventually, you're going to only settle with one. Make sense so far?
It makes sense, but I still don't understand how this ties in with the
I haven't covered
the looping variable. Okay. So then I'm
almost
waiting
like
for that.
this almost like a loop, but the bodies can be different, right? It's like you have to, because in the code, you have to unroll all of them, right? Because this, you can generate the locking script for this one, and then eventually you can concatenate them all. That's
I see. So you're kind of on your side.
Mm-hmm.
On your side, when you're doing the compilation, it's basically probably like one unlocking script, but it just has a bunch of different case. It's like a case statement where you have a bunch of different things.
It is.
And so then as you add, then as you add more of these, then it's like a potentially infinite loop.
Yeah, it can becomes huge. And here's a bad thing, right? You are not going to use all the branches all the time, because if it's not, if it's just it's not a stateful contract, you just call it once and you are done. So what do? It's a similar idea. You can, you can break this almost like monolithic contract into multiple smaller contract, and you can use this as a main contract. The main contract, again, for example, here, right, you have 4 branches, and then you can just you can put each branch in its own contract, and then you can hash them all, and then you got four hashes here, right? Then you can use the same idea when we have for the pay to contract hash, you can call this contract from the main contract. But in this case, you can dynamically, if you are using branch A to unlock it, you can call branch A. If you are unlocking with branch C, you can load branch C, right? You're only choosing one, whichever is going to be used eventually. You are not putting everything, all the branches in the main contract, and then bloating it. It
but you still get the advantage. But you still get the advantage of having like a contract that looks like the main contract, where it has all these different options. But then when you're calling it, then you're able to do it in a more efficient way.
Yes, you only, because as I said, right, you're only going to use one way to unlock it. So that's going to be what is here.
Yeah, because the alternative, I could have said, well, why didn't you just break it up into all these different smaller contracts to begin with? But you want the user interface advantage of having a main contract with all these options, perhaps, instead of a bunch of these smaller contracts. And so then by using this technique, you can still have that large main contract with all the options, but now you still get the performance advantage.
Yeah, exactly.
as if it was broken up.
Otherwise,
Okay, got
yeah,
it.
if you don't have this diagram, it will be like this contract. You have all the branch A, B, C, D. It's all it's all included in the gigantic monolithic contract, right? Which is usually is big, right? And even you are putting 4 options there, eventually you are going to only have to use 1, which is waste, meaning the others, is wasted, right? But here's the thing, if you don't put them, you don't know how the user is going to unlock, right?
Mm.
But here you have basically you combine the strengths of both words. You can have many options, but also you don't have the unnecessary bloating issue. Because you can,
Cool.
which branch you are using, you can just reference it, almost like a dynamic thing. Because for example, branch A, you just put branch A. Then B, C, D, they don't end up on chain at all. Make sense?
Got it. Yeah, it makes sense.
Yeah. So this is only 2 of the most prominent ways you can save using the pay to contract hash idea. One is loops, and the other is when you have many public functions to unlock. But there may be other cases you you kind of have to know it in the compile time, but also it's very dynamic. So you can abstract, you can take out the part that's causing a lot of bloating and put in another contract, and then you can reference it using contract hash. So I think, yeah, that's the basic idea. Any other comments? That's basically what we want to cover in this week.
That makes sense. But now I'm curious, and we don't have to cover it now, but so contract hash, and then why is it the contract hash? Maybe I should go review the old part, but so you're taking this contract and you're taking a hash of it, and then, but why, I guess why?
Because if you, I think, yeah, here's the way. There are 2 ways. Yeah, if you don't, first of all, we can talk about pay to contract, right? Basically, you can call another contract. Then how do you know the contract is what you want? One way is you hard code the whole contract, right? It can be like 1,000 bytes. It can be 1 million bytes or 1 terabytes. How do you compare? It's like you are referencing something, right? You have to give it ID. Of course, the thing itself can be the unique ID, right? You can compare byte to byte. That's one way, right? But that's not efficient because now you have 2 copies. You have the one that's brought in from another input. You also have the one you hard code in the main contract to compare it against, right? This means you have 2 copies. So it's not efficient. That's why you hash it, right? Because hash is like a unique idea of something, like a fingerprint or digest, right?
And it's small.
And it's small, yes. And another benefit, I think we talked about in the pay to contract hash episode, is the hash. If you remember, the number 1, at least for today, the contract used today, what it is on the Bitcoin main network.
Which contract is the most? Is it pay to public key hash?
Exactly. It's not pay to public key, right? Pay to public hash. Another benefit is we are using, if you remember, we use the same hashing algorithm, which is hash 160. So that means when you're referring, if I give you only this hash, you can now tell me whether it's derived from some private key, public key, or it's derived from some contract, right? The contract, if it's derived from contract, that means there's no private key behind it, right? You're coming from a Solidity, right? Ethereum background.
I mean, I wouldn't say.
You have
people
knowledge.
always assume that, yeah.
Okay, you have
a little
knowledge.
bit, yeah.
Okay.
Yeah.
I know you're now trying to distance yourself from that, but okay, you know it. Right? In Ethereum, you have two types of account. One is they call it externally on account. Basically, the user, right? You have a private key, and then you derive the account address. The second is a smart contract. It's not controlled by private key. It's the same thing here, right? If I give you this hash, it's derived from private key. It's owned by some user, right? If I just give you the contract hash, it's similar to them, the smart contract account in Ethereum model. It's not controlled by a certain individual having the certain keys, right? It's controlled purely by logic inside the contract code.
Got it. And can you tell by looking at the hash?
No, I can just give you a hash, right? You don't know whether it's derived from public key, because unless you are breaking like a asymmetric public key cryptography, otherwise it's impossible. It's the same with Ethereum, right? If I give you just this address, you don't know whether it's user account or it's purely like a contract account. You don't know, right? Same here. So that's why we choose this specific hash to be consistent. So you can not only, interface wise, when you are transferring, let's say some tokens, you can transfer it to some user or transfer it to this contract. You cannot tell, right? You don't have to differentiate. The user don't have to care anyway.
Cool, makes sense.
Yeah, strongly, I think this is all connected to whatever we have covered before. I think I'm going to share in the show notes. Basically, you have the pay to contract hash, you have inter-contract call, and you have the latest one. How do you split it using pay to contract hash? So people can know more about if they want to know more about the details, how it works, I'm going to put it in the show notes.
Cool.
Okay. Seems, yeah, we can keep it compact. I think 1 week we want to focus on something specific. Any other questions regarding this or anything else?
No, but I'll look into this, and yeah, I mean, it makes sense.
Yeah, it is this, I could say this to be widely used, because before I wouldn't say it's a bug, but it's kind of like a pain to use it, because if you have a big loops, but most time you don't have to, let's say you have, in the average case, you have to loop, let's say 10 times, but in the worst case, you can loop up to, let's say 1,000 times, right? But because we don't have a dynamic looping, right? Like a for loops or while loops. So you have to always use the worst case. That means you have to always use the 1,000 thing, which means even you are only loop 10 times, you have to, in the locking script, you have to use 1,000, which is not ideal, right? Especially loops get bigger and bigger as we keep scaling. So this technique is, I think some people comment, is it brings you to the same efficiency level as other non-UTXO based blockchains, because you kind of now almost have a while loop or for loop, but it's not a language construct. You are using this pattern to achieve the same thing. So I would imagine this is going to be widely used in production more and more. Okay, sounds good. All right. Okay, let's keep it tight, and glad you are back again. Okay, see you next time. Okay.
All right. Yeah. I'll see you.
Okay, enjoy the rest.
Bye-bye.
Okay, bye-bye.
You too.